Some very familiar notions of physics are completely overturned by Einstein's theory of special relativity. As the first example, we'll take the relativistic addition of velocities. Now, imagine that there's a mosquito moving with respect to the ground, and let's say I'm fixed, and the mosquito is moving towards you at 3 centimeters per second. And let's say that you are moving in the direction of the mosquito as well at 1 centimeter per second. So what's the speed with which you will see the mosquito moving at? You'd say 2 centimeters per second. Is that how it works out in special relativity? Let's take a look. Let's begin with the Galilean addition of velocities. Here there will be only one universal time. Here are two frames that are moving apart from each other at speed v. There are two observers. The distance between the origin of the first and the origin of the second is increasing with time, and that distance is v times t. Obviously here v has to be a constant. Now, let's suppose that an event happens. Well, obviously this event will have coordinates in s and in s prime. In s, the coordinates will be the time t at which it happened, x and y. X is this distance from here to here, y is this distance. And now in s prime, there will be t, because t prime and t are the same, x prime and y prime. X prime is this distance from here to here. Y prime is the same as earlier. And so what we have is x prime is equal to x minus v times t. Y prime is the same as y, and t prime is t. There's only one universal time. Now, if there's a small change or a second event, which is close to the first, then delta x prime will be delta x minus v delta t. And now this delta t is the separation in time between the second and the first event. Now I'm going to put a body into motion along the x-axis. As it moves along, its position and time is recorded. I'm going to call the separation in x between here and here delta x, and this is as observed by this observer in the frame S. And now the separation in time between these we shall call delta t. So delta x by delta t is what we would call the velocity in the x direction, ux. Now, looked at it from his point of view, ux prime would be delta x prime divided by delta t prime or delta t, which are the same. And now delta x prime is delta x minus v delta t divided by delta t. And so this gives us ux minus v. And so we have the usual Galilean transformation of velocities, that is to say ux prime is ux minus v. And of course, if this object is traveling at speed v in this direction, as is the observer, then ux prime will be 0. Let's now consider exactly the same circumstances, but this time we shall consider the relativistic addition of velocities. So either this frame is moving very, very fast in this direction, or this red body is moving fast. Now let's let the separation between the event here and the event here be delta x as recorded by S, and the separation in time be delta t. So that's ux as before. But now let's look at it from his point of view, that is to say in the frame S prime, where ux prime then will be delta x prime divided by delta t prime. But here we shall use the Lorentz transformation equations. So delta x prime is gamma delta x minus v delta t, and delta t prime is gamma into delta t minus v over c squared delta x. Of course, the gammas cancel. And now let's divide the numerator and the denominator by delta t. So I'm going to divide this by delta t and divide this by delta t. We see from here that this becomes delta x by delta t minus v divided by 1 minus v over c squared delta x divided by delta t. But delta x by delta t here and here is ux, that is to say, the velocity as observed in the S frame. So we get ux minus v divided by 1 minus v into ux over c squared. This numerator is exactly what we had obtained for the Galilean transformation, and you can see that if we put c equal to infinity or c very, very large so that this term over here becomes negligible, in that case ux prime will be ux minus v. So we'll get back to the Galilean transformation in that case. Let me now use the same formula but in a different situation. Well, first of all, let me write the velocity. Ux prime is ux minus v divided by 1 minus ux into v over c squared. So it's only the denominator which is different from the Galilean case. Now, what if ux is equal to c? In other words, if this particle, according to this observer, is moving in this direction at speed c. Well, ux prime then will be c minus v divided by 1 minus c into v divided by c squared. One of the c's cancels, and so this is c minus v, which cancels at the top, and so this is equal to c. In other words, this observer, S prime, will observe this photon coming towards him at speed c, the speed of light. And that's exactly what one expects, because the speed of light, according to the postulate of relativity, has to be the same in all frames. And so this is a consistency check upon the formula that we just derived. Consider now the situation where the frames are, as before, moving along the x-axis, but the particle is moving along the y-axis. The first event and the second event happened at the same value of x. Let's now look at the two events. The first when the body was here, and second when the body was here. Well, obviously they're at the same value of x, so the separation delta x is 0, and the separation in time, if we call that delta t, if we divide then by delta t, that's still 0, and that's the velocity in the x direction. The velocity in the y direction, uy, will be delta y by delta t. So these are the x and the y components as viewed in the frame S. Now let's go to frame S prime. In frame S prime, ux prime will be delta x prime divided by delta t prime. Now delta x prime is gamma into delta x, which is 0 from here, minus v delta t, and delta t prime is gamma into delta t minus v over c squared delta x. But of course delta x is 0. And the gammas cancel. What we have over here then, and of course this delta x is 0, so what we have is minus v. In other words, this observer will see this particle moving this way at speed minus v. What about uy prime? For uy prime, we need delta y prime divided by delta t prime. But delta y prime is exactly the same as delta y because transverse lengths are not changed. And delta t prime is gamma into delta t minus v over c squared delta x, but that delta x is 0. And so this is just equal to 1 over gamma delta y by delta t, but that's uy. Now this result is very easy to understand because from the point of view of this observer, the clocks in the frame S are moving slow. So this body also appears to move slower. That's just because time has slowed down. And now finally, we will consider a body that moves both along the x and the y directions. In this case, both delta x and delta y are non-zero. So here ux, which is delta x by delta t, and uy, which is delta y by delta t, are both non-zero. And of course, delta x is the difference of the x-coordinate of this event and of this event. So it's this much, and delta y is this much. Delta t is the time needed to go from here to here. Well, let's calculate now uy prime. That's delta y prime by delta t prime. And now this is delta y divided by gamma into delta t minus v over c squared delta x. Now let me divide this by delta t and this also by delta t. And so the numerator is uy, whereas the denominator is gamma into 1 minus v over c squared. And now delta x by delta t is ux. So this says that the y direction velocity observed by him will be the y direction velocity observed by this observer divided by gamma into this factor over here. Now similarly, let's work out ux prime. So ux prime is delta x prime divided by delta t prime, and now this is gamma into delta x minus v delta t divided by gamma into delta t minus v over c squared delta x. Again, let's divide this by delta t and this by delta t. Taking the delta t inside gives gamma into ux minus v divided by what we see over here. Now this gamma has cancelled out. what we have at the bottom is 1 minus v into ux divided by c squared. And now this is the formula for the x component of the velocity as observed by him. Let me quickly summarize the formulae that we've derived for the relativistic addition of velocities. Here there will be 3 dimensions, x, y, and z. And now suppose that there's some object that's moving with respect to this fixed observer, and the components of velocity are ux in the x direction, uy in the y direction, and uz in the z direction. If there's another reference frame S prime that's moving towards the right at speed v, then what we derived was that the velocity in the x direction that's observed in the S prime frame is ux prime, which is ux minus v over 1 minus uxv over c squared. Then, if we define the gamma factor as usual over here, in that case, uy prime and uz prime are then calculated as follows. Now notice that it's the same factor in the denominator in all 3 components, ux prime, uy prime, and uz prime. Also notice that you have the factor 1 over gamma for uy prime and 1 over gamma for uz prime. And that's because when you look from the frame S prime towards S, then the clocks in S will appear to be moving slower, and therefore all speeds in the transverse direction will also be slowed down by this factor 1 over gamma. And finally, here is our usual observer, and now the difference is that the frame S prime will be moving in any direction. That could be an arbitrary direction with speed v. In that case, for velocities in the same direction, this will be our new x prime direction, we'll use this formula, and for velocities that are transverse to this, we'll use these formulae. Now for the case of an arbitrary direction of the velocity, we can easily write down the formulae that will replace this. Remember that this is for motion only along the x direction, but we won't do that over here. Let's now solve the following problem. Here is an observer fixed to the ground. He sees one rocket ship that's moving towards the right at speed 0.9 times the speed of light, and a second rocket ship that's moving towards the left, also at the same speed. The first part of the question is, what is the relative speed of the 2 spaceships as observed from the ground? Now that's easy, because the relative velocity is the difference of the 2 velocities, so it's 0.9 c minus 0.9 c. This is minus because this rocket ship is moving in the minus x direction, and so that is 1.8 c. But now you might think that this violates the principle of relativity. After all, what speed could exceed the speed of light? But here the point is that this is not the speed of some material object that is moving. This is just something mathematical. It's the difference of 2 speeds. And there is no restriction at all on this being less than c. The point is that a material object cannot travel faster than the speed of light. Now let's come to the second part. We are asked what is the speed of the second spaceship as observed from the first. Okay, we'll call this the first spaceship and this the second. Now imagine that we are traveling with the first and we are looking towards the second. Okay, So in that case, we will use the formula that we derived. Ux prime is ux minus v divided by 1 minus ux into v over c squared. Now, v over here is minus 0.9c. Why is that? That's because if we are traveling with this reference frame, then this reference frame here is traveling towards the left at speed 0.9c. In other words, minus 0.9c is the velocity. Then we also know that the speed that is observed in this moving reference frame, moving with respect to this, of course, is minus 0.9c. So this ux prime, which is the speed observed in the s prime frame, is then minus 0.9c as well. Okay, so now let's put this into the formula up above over here, and so we get minus 0.9c equals ux, and ux is what we want, minus v, but v is minus 0.9c, so this is plus 0.9c, and at the bottom we will have 1 plus 0.9 ux divided by c. Now from here, by taking the denominator over to the other side, we have minus 0.9c minus 0.81 ux equals ux plus 0.9c. And so taking this term over here, what we get is 1.81 ux is equal to 1.8 c. And from here, obviously, ux is 1.8 over 1.81 c. And if you work that out, that's 0.994 c. In other words, if you're traveling with this spaceship, then you will see this spaceship approach you in this direction at 0.994 c. On the other hand, if you're traveling with this spaceship, then you will see this one approach you at the same speed, that is 0.994 c. So although the Galilean addition of velocities would have told you that this observer would have seen 1.8 c, in actual fact, he sees 0.994 c. There's a big difference. And this is what happens when velocities get close to that of light. The Doppler effect for sound is something that is very commonly experienced. So if you are standing in front of an ambulance that is coming towards you, the frequency of its siren is increased. Whereas if you're standing towards the other side, towards the back, the frequency is decreased. The reason the frequency is increased if you're standing in front is because less time is needed between the peak of one wave and the peak of the second wave. The same situation holds for light, and now we will examine this in some detail. In considering the relativistic Doppler shift, we will place a source of light in one frame. Let's call this the fixed frame, and this light will come out in sharp pulses. Those pulses of light will move towards the right and be observed by the observer in the moving frame. Suppose these flashes occur after every t seconds. So then the frequency is defined as 1 over t. Now consider the fact that when a pulse of light goes towards the right, this frame is moving away, and so it's going to take longer for that flash to reach the origin over here, which means that effectively there will be a wider gap in time between the pulses, and hence the frequency, which is 1 over the time, will appear smaller, reduced in the moving frame. But let's analyze this properly. So let me first make two columns, one of sent events and the other of received events. Now, the first event that occurred was at time t equal to 0, at position equal to 0. So a flash of light was sent out at time t equal to 0 to the right. And let's say that this was received at time t1 at position x1. And these are coordinates as measured in the frame S. Now let's calculate t1, assuming that at time t equal to 0, there was a distance d between the two frames. So clearly, the time t1 is the total distance traveled, let's call that x1, divided by the speed of light c, but x1 is the initial distance d plus the extra distance traveled in time t1. So it's d plus v t1 divided by c, and now if you take t1 on that side, you can see that t1 is equal to d divided by c into 1 minus v over c. And from here, x1 is equal to ct1, and so therefore x1 is d over 1 minus v over c. So now we have the coordinates of the first event, t1, x1. That's the event where the pulse of light was received at the origin of S prime. Okay, now let's take the second pulse, which is sent out at time t equal to t, and again position x equal to 0. So the pulse leaves at time t equal to t and arrives over here at time t2 at position x2. x2 because this frame has moved on. Okay, so clearly t2 is the beginning time, which is t, that's the time at which the pulse was emitted, plus x2 over c, that's the time taken to travel the distance x2, and x2 will clearly be the initial distance plus vt2 divided by c. From here, we get t2. That's quite easy. Just take t2 on this side over here, and so you get t2 is d over 1 minus v over c into c plus t over 1 minus v over c. And then, of course, from here, x2 over c plus t is equal to t2, we get x2. So x2 turns out to be d over 1 minus v over c plus ct over 1 minus v over c. So now we have the coordinates of this event, t2, x2. This is the second event, meaning the second time that the pulse is received at the origin of S prime. From here, obviously delta t, which is the separation in times, t2 minus t1, that's t over 1 minus v over c. And similarly, delta x, which is the separation in positions x2 minus x1. So remember that this frame S prime has moved on, and this separation x2 minus x1 is got by subtracting x1, which is over here, from here, and so obviously this is Ct over 1 minus V over C. Now these are the separations delta t and delta x as measured in S. Now obviously they measured at the same point here in S prime, and so delta x prime is 0, but delta t prime will not be 0, certainly. Delta t prime, we know what that is when we use the Lorentz transformation. It's gamma into delta t minus V over C squared delta x. And so let's simplify this a bit. This becomes gamma times t, and inside one gets 1 minus V squared over C squared divided by 1 minus V over C. Now 1 minus V squared over C squared is 1 minus V over C into 1 plus V over C, and so this is equal to gamma t into 1 plus V over C. So now let me go over here. Delta t prime is then gamma, but gamma is 1 over square root of 1 minus V squared over C squared, and then there's t into 1 plus V over C, and so obviously this simplifies to the square root of 1 plus V over C over 1 minus V over C times t. Now this V over C is what we call beta, and from here therefore we get nu prime, which is 1 over delta t prime, and therefore nu prime is 1 minus V over C over 1 plus V over C times 1 over t. But 1 over t is nu, that's from here. And so we've got this formula here for the Doppler shift, the relativistic Doppler shift. What this is saying is that if the frequency in the rest frame of the source was nu, the frequency in the moving frame will be nu prime, and it's going to be less than nu because 1 minus V over C is going to be less than 1, and this will be greater than 1. So physically one understands that if the observer is running away from the source, then he will observe a smaller frequency. On the other hand, if he's running towards the source this way, then V over here will be negative, in which case this over here will be 1 plus something, and this will be 1 minus something, in which case nu prime will be bigger than nu. So we say that an observer who is running away will see light that is red shifted, whereas an observer who is running towards the source will see light that is blue shifted. That's the Doppler effect. Let's work out a problem that concerns the relativistic Doppler shift. We'll imagine a world where the speed of light is much, much less than the actual speed, so it's just 610 kilometers per hour. But the speed limit for a car is the normal one. It's 120 kilometers per hour. Red light corresponds to a wavelength of 6,000 angstroms and green light to 5,000 angstroms. So of course, the red light then will have a frequency, let's call that nu, which is the speed of light divided by 6,000. This is what you learned in elementary physics. And similarly, the green light is frequency c over 5,000 angstroms. Now let's remember our Doppler shift formula. So if the observer is heading towards the source, the frequency will increase. And of course, it doesn't make a difference whether it is the source which is moving towards the observer or the observer moving towards the source. By the principle of relativity, both of these are indistinguishable situations. We did learn that the frequency which is observed will be 1 plus v over c divided by 1 minus v over c times nu. So if the frequency in the rest frame of the source is nu, the frequency in the frame in which it is observed will be nu prime, and in this case, that frequency will be greater than nu because it is multiplied by this factor. Now let's remember the physical reason for why this frequency is going to be bigger than this. That's because as the observer runs towards the source, the light that comes out will have to travel shorter and shorter distances as this moves closer and closer. Okay, now let's put in nu prime equals c over 5,000 and nu equals c over 6,000. And so we get 6 over 5 is equal to square root of 1 plus v over c divided by 1 minus v over c. Squaring both sides, this gives 36 over 25 is equal to 1 plus v over c over 1 minus v over c. And now take this to this side. So we get from here 36 minus 36 v over c equals 25 plus 25 v over c. And now take this on this side and this on this side. So we get 61 v over c equals 11. And so from here we get v over c equals 11 over 61. And so that gives v as 11 over 61 times c. C is 610 kilometers per hour. And so that's 610. And that makes 110 kilometers per hour. Now, that's less than 120 kilometers per hour. And so he should not be punished. He, in fact, is telling the truth that even though, according to the policeman, the light was red, yet what he saw was green. Let's consider the relativistic Doppler shift once again, but this time the observer will not be running away from the source, but rather will be moving perpendicular to the source. What this means is that the distance from the source to the observer is going to be pretty much constant, as long as the motion of the observer is perpendicular to the line connecting them. Let's make a table of events. So the first pulse is sent and then it is received. So we'll make a little table over here. Let's say the first pulse is sent at time t equal to 0 from position x equals 0 here. And it is received over here at time t1. And let's say that the distance from here to here is d. Now clearly t1 is just d divided by c. Let the second pulse now be sent at time t equal to t. And of course, it's also sent from the same place, x equals 0. Suppose it is received at t2. And now this distance from here to here has not changed. It's still d. And so t2 will be the time at which the pulse started out, plus the same time d over c, which is the transit time. And so therefore, the difference delta t between t2 and t1 is just t itself, capital T. And of course, delta x is 0. Now the Lorentz transformation says that delta t prime is gamma into delta t, which is capital T, minus v over c squared, delta x, which is of course 0. So that's 0, this is t, and so this is gamma t. The frequency, nu prime, is 1 over this, so it's 1 over gamma t, and now 1 over t is nu, so this is then nu over gamma. And so we've reached the conclusion that the received frequency will be the emitted frequency divided by gamma. That's actually very easy to understand because from the point of view of this observer, the clocks in this frame S, so this is S and this is S prime, have been slowed down. There is a relative velocity between S and S prime, and this gamma is the usual 1 over square root of 1 minus v squared over c squared. The only difference now is that this is moving in this direction with speed v. This is called the transverse Doppler effect, and it's a purely relativistic effect. It comes from time dilation. And of course, it has been checked many times. It works perfectly. In this lecture, we learned how to add velocities relativistically and also do the Doppler effect relativistically. All we needed was the Lorentz transformation. In the next lecture, we're going to use the same Lorentz transformation, but we're going to write it down in a slightly different way. That's going to prepare the way for us to talk about vectors and then later tensors in special relativity.